All right, if you haven't yet picked up that glucose transport and glucose homeostasis is a key theme in this course, this is going to help sort of solidify it. Thinking about how we get glucose in and out of cells and in and out of organelles as are sort of needed to facilitate sort of glucose homeostasis. So when we talk about transporting glucose, there's lots of different transporters that we will see for transporting glucose, including a separate video on the sodium glucose transporter that we're going to see in our intestinal cells. But this slide is focused on glucose transporters that we generically just refer to as GLUT transporters, the GLU for glucose, T for transporters. And what we're going to see with glucose transporters is we're going to see a number after them. There's multiple sort of isoforms of these glucose transporters. Remember, isoforms or isozymes are proteins or enzymes that are found either in different locations or are differentially regulated. Okay, so let's actually write that down here because we can talk about, we're going to see here GLUT2 and GLUT4 transporters, and they're what we refer to as isozymes or isoforms. So this slide is going to talk to us about GLUT2 and GLUT4. Okay, these are going to be what we refer to as isozymes, okay, or isoforms, okay? And that means that these are proteins or enzymes that perform the same function but are differentially located and or regulated. So they perform the same function but are differentially located and or regulated. And what we're going to see here is that it's both of those situations for these two different glucose transporters. So some commonalities for what we see with glucose transporters, no matter what the number is after that GLUT prefix, is they are passive mediated. That's the type of transport. That means we are going to be moving things from high glucose concentration to low. We are going to be dissipating proton gradients, okay? So what I'm going to do here is I'm going to compare and contrast GLUT2 and GLUT4 transporters, but let's take a look at this picture first, just so that we can understand sort of the mechanism for how glucose transporters work. And why this is interesting is glucose is not a small molecule, right? Got my glucose molecule here. It's not a small molecule. It's not like an ion or, a small sort of couple of atom small molecule, right? It's a fairly sizable molecule. And so how do you let something big like this in and not have a gaping hole that's going to let other things in? So many transporters are going to work like this. What's going to happen is as this glucose is floating around sort of an aqueous environment, it's going to be hydrated by water. We talk about this in our potassium ion channel, like having bubble wrap that's sort of surrounding our molecules. In an aqueous environment, we're solvated by our solvent, which is water. And so we need to, in order to have most of these ions, molecules sort of get transported across our lipid bilayers, we need to remove that bubble wrap, take that water off so that they can fit in where they need to fit in. Now, the problem with many of these transporter systems is it takes energy to take that bubble wrap off. It takes energy to desolvate biological compounds or ions. That's an enthalpic penalty. Unless we recover that energy with an enthalpic compensation by forming new interactions when it binds to wherever it's going to interact, then it is an energetically unfavorable system and process. So we're going to see that multiple times over here. But so again, here we've got our glucose molecule that's solvated by water, our bubble wrap. Once we take it off, it's going to be able to bind to, and I want you to think about if this is this picture of the glucose transporter, it's open on one side, closed on the other, and then as it binds glucose, it's going to open on the other side and allow glucose to come off. Okay, so what's going to happen, and I'm going to try to show that with my molecule here. You can see here's glucose. You can see that there's some oxygen atoms that we sort of have here. Okay, this is probably sort of that exocyclic CH2OH group there, right? We've got that right here. So I'm going to sort of try to demonstrate that here. Glucose has our bubble wrap on it. We take that bubble wrap off, and then it's going to be able to bind into my glucose transporter. That's going to cause, so I'm binding in here. I'm forming new intermolecular forces that make this process favorable. I'm going to compensate for the unfavorable process of desolvating glucose. Now, once I form these interactions, I'm going to have a conformational change. My transporter is going to close on this side and it's going to open on the other. Okay, and then again, my glucose, I didn't want to drop it there, is going to fall out. Okay, it's going to get moved to the other side. So the motion of my transporter is really open. I bind substrate, conformational change, substrate goes out on the other side. In this case, the substrate is glucose. So we sort of see that here. I've got an open glucose transporter to the outside of the cell. Glucose binds to the protein. Okay, so here I can see glucose binding, right? New intermolecular forces there. I'm going to then have this transporter open on the other side. Glucose is going to dissociate on this side and it's recovered, right? Now we're going to have another conformational change that allows it to repeat that binding and transporting event. So that's how all of these glucose transporters work. I'm going to highlight here that right now it shows a glucose transporter that is within the lipid bilayer. There are some glucose transporters that permanently reside in the lipid bilayers of certain cell types. What we're going to see, though, is for some glucose transporters, for example, GLUT4, it is not always present, but what happens is you'll have a little lipid bilayer vesicle that contains a bunch of these transporters, and only when it receives a chemical signal does it fuse with the lipid bilayer and then display or put those transporters on the surface. So right now, this is what the glucose transporter needs to look like in the lipid bilayer in order to be doing that transport. But not every glucose transporter resides permanently. Some of them are delivered in vesicles as needed to be displayed on the surface, and then when not needed, they're withdrawn back in. And we're going to see that case with both GLUT2 and GLUT4. Okay, so let's sort of highlight what we see here with GLUT2 and then GLUT4. So we're going to take sort of a shallow dive, if you will, here on how these transporters work. We're going to take a much deeper dive next semester when we understand glucose metabolism and then glycogen metabolism, both of those related to glucose homeostasis. But we're introducing these here so that we can build on these constructs later. So I'm going to sort of go back and forth, compare and contrast between these so we can sort of understand how they both work. Okay, and so I'm going to start with where these are located, right? We said these are isozymes. These are differentially located. GLUT2 is found in your liver and your pancreas, whereas GLUT4 is found in your muscle, skeletal muscle particularly, and adipose tissue. Okay, so GLUT2 transporters are always present on the cell surface. So always present on the surface. Okay. And importantly, they are insulin insensitive. So insulin insensitive. Okay. Contrast that to our GLUT4 receptors, okay, which are insulin sensitive. Okay, so this is where we are going to have an increase in insulin levels, are going to facilitate the fusion of that vesicle that contains those GLUT4 transporters, and it displays them on the surface. So we only get to this glucose transporter on the cell surface lipid bilayer when we've got insulin present. Okay, so differentially located, and now we're going to talk about how they're differentially regulated. It has to do with why one is insulin insensitive and the other one is insulin sensitive. So when we think about how these are differentially regulated, these are really transporters that bind a molecule. So we can think about Km values for these. Remember what Km values are. They represent the affinity of a substance for its receptor. So in this case, for glucose, for the glucose transporter. And you can think about, in terms of a halfway value, what is the concentration of glucose we need to be at for these to be sort of operating and transporting at half of their efficiency, binding their substrate sort of with half efficiency. So What we see for GLUT2 is it has a high Km value. And just defining again, because we talked about it, the Km value you can think about as the affinity for your substrate, and in this case, that substrate is glucose, okay? And here's where this value is. It's about 15 to 20 millimolar. Remember what that magic number for glucose is? 5 millimolar. That sort of baseline glucose homeostasis level. You don't want blood glucose levels falling below 5 millimolar. Above that, that puts you into a fed state, and we need to be doing something with that glucose. So again, we can think about this Km value just to kind of highlight again. This is going to be the concentration that you need to have for half of your molecules to bind. Okay? And this is really an important piece here, because remember, these glucose transporters are constantly going to be moving glucose from high concentration to low. So they're essentially always an open channel, and if glucose concentration in the bloodstream is high, it's going to be pulling it into the liver, pulling it into the pancreas, right? Again, we need to have that pancreas have that glucose signal so that it produces the insulin from its beta cells, puts that out into the bloodstream to facilitate the next piece, which is the GLUT4 transporters. But we want to make sure that when that blood glucose level falls back down to normal levels, falls back below, in theory, even 15 or 10 millimolar, that we are not having the liver pull in that glucose. And why that's important is that could create a state of hypoglycemia. We need to maintain 5 millimolar blood sugar in our blood, right? And so if we have transporters that are just pulling it in too greatly, we can create a state of hypoglycemia. We'll talk about medical situations where that could actually be happening, but we want to make sure that that doesn't happen for a transporter that's always there. So GLUT2 is always there. We need to make sure that it is not operating when blood sugar levels are lower. And how that is facilitated is not by sort of its presence, it's by its binding affinity. Okay, so let's talk about the GLUT4 receptors then. These ones are insulin sensitive. So again, what happens as your blood sugar levels rise? Your pancreas secretes insulin, and then that is going to be the signal to fuse intracellular vesicles that are full of these GLUT4 receptors. They're going to fuse with the membrane surface, and they're going to display these GLUT4 transporters on the surface. Now, if you had to predict, you might say that we could have a lower Km value for these transporters because they're only going to be put out there when we have high blood sugar. They're not going to be present when there's low blood sugar. So we don't have to worry about these facilitating hypoglycemia. So in this case, we do see that they have a very low Km value, less than or equal to 5 millimolar. Okay, and again, they are only going to be present when we have high glucose, but that's going to allow us to try to decrease the concentration of glucose. So again, only present with high levels of glucose. So they're going to essentially like serve as a giant vacuum to sort of suck in glucose from the bloodstream. But remember, these are only going to be operational to a certain max capacity. So because remember, when we pull in glucose into skeletal muscle, we are going to be making it into glycogen. And so to that end, once we've tapped out and filled up our glycogen reserves in our muscle, we can't take in any more glucose. So it's going to stay in the bloodstream. And that's, again, when you're going to have your liver be able to produce it into fatty acids and then triglycerides for storage in adipose tissue. So again, we need to make sure that we are adequately muscled. So let me just write this down here. Let's see, when our glycogen reserves are maxed, right? Then we're not going to be able to pull in any more glucose. But we've talked about skeletal muscle being a glucose sink, right? It is a great way to try to mitigate sort of blood sugar levels, right? But that's why it's important that you are insulin sensitive, because If your skeletal muscle is becoming insulin resistant and you're not listening to that signal, you're not going to be able to deposit that excess glucose into your skeletal muscle. You're not going to be able to replenish your glycogen reserves. Your cells are going to be thinking that they're starving, sending out extra signals to your bloodstream to try to provide energy, when in reality you don't need it because there's plenty of blood sugar that's out there. So again, threads that we see in this course are glucose homeostasis and, importantly, insulin sensitivity. So again, an introduction to GLUT2 and GLUT4 glucose transporters.